In this video, we're going to be solving systems of linear equations. Remember, a system of equations is a collection of two or more equations, each containing one or more variables. So for example, this is a system. 2x plus y equals 3, and y equals x minus 3. And when you solve a system, the goal is to find the solutions that the equations share. This equation here has an infinite number of solutions. This equation has an infinite number of solutions. We're trying to find the solution or solutions that they have in common. We have numerous ways of solving systems. In this video, we're going to review 3 strategies. We're going to talk about solving by graphing, solving using the substitution method, and solving by using the elimination or addition method. So let's jump in. We're going to solve this one by graphing. Remember, a graph just shows you a picture of the solutions for a particular equation. So if we graph this equation and we graph this equation, we'll have a picture of their solutions and we're going to see what they have in common. Now, if I do this neatly, I should be able to do this even freehand. Let's graph this first equation. We have 2x plus y equals 3. Let's solve for y. So we have y equals negative 2x plus 3. So if we use our slope and y-intercept, we could get a pretty decent graph. So let's see, our y-intercept is 3. And our slope is negative 2. So that means I go down 2 over 1, down 2 over 1, and I would have a graph that looks like this. Now my second equation, let's see, let me label this. This is 1, this is 2, this is 3. My second equation is y equals x minus 3. So it's already in slope-intercept form. The y-intercept is negative 3, so negative 1, negative 2, negative 3. And my slope is 1, so up 1 over 1, up 1 over 1, up 1 over 1. A little bit off here since I didn't have a graph paper. But here are my 2 lines, and notice they intersect right here. And even on this one freehand, we get a pretty good look at what the solution would be, the point that they share. It looks like it's over 2, down 1. So the point 2, negative 1 seems to be the solution. Now the nice thing about a system of equations is it's easy to check to see if you have a correct answer. We can pop the disordered pair into both equations, and if it works, we know we have a solution. So if we put 2, negative 1 into the first equation, we have 4 minus 1 equals 3, which we know is true. And if we substitute that 2, negative 1 into the second equation, negative 1 goes in for y, 2 goes in for x, and we have negative 1 equals negative 1. So that is also true. So we have confidence that 2, negative 1 is in fact the solution for this system. Let's look at this next one. Let's solve it by graphing as well. So this first one is, the first equation is y equals 1/2 x minus 5. So let me draw a picture of this one. My y-intercept is at negative 5. My slope is 1/2. So up 1 over 2, up 1 over 2. And I have a line that looks like this. Now that's the graph of this first equation. Now the second one, We can use x and y intercepts if we like to graph it, or we could solve for y. Let's solve for y for this one. X minus 2y equals 2. So that means we subtract x. Divide by negative 2. And then we could graph this one, but you may see what's coming right now. Notice the slope of the first equation was 1/2. The slope of this equation is 1/2 as well. So when we graph it, y-intercept is -1. The slope is 1/2, that's up 1/2. And if we graph it, we see that we have a pair of parallel lines. That means they don't share any points. And we would say there is no solution to this system. It is called an inconsistent system if there is no solution. But if somebody asked me to solve the system, I would say there is no solution. That would be my answer. Let's look at one more by graphing. And we'll look at this one. Our first equation is already in slope-intercept form, so our y-intercept is 1. Our slope is 1/3, so up 1/3. Up 1/3. And we could draw our line. Let's see, it went over 3 here, be it -3. So there's a graph of our first equation. Now the second one, again, I could solve for y, but let's do this one differently. Let's graph it by finding the x and y intercept. I'll just remind you that that's another way to graph an equation, especially when we know it's linear. So here's my equation, and I want to find the x-intercept and y-intercept. Remember, to find the x-intercept, you set y equal to 0. Well, we get an x-intercept pretty quickly this way. So we get x equals -3. So for this particular equation, its graph would have an x-intercept of -3. Hey, that's the same as the previous one. Oh, yeah, x equals -3. How about the y-intercept? For the y-intercept, we make x as 0. And if we do that, we are looking at -3y equals -3, or y equals 1. And hey, that point was on our previous graph as well. And in fact, what we see is we have exactly the same line. So these two equations are actually equivalent. They both have this as their graph. So the solution is the set of all points that are on this line. So for now, I'm just going to say there are infinitely many solutions. There are other ways of answering this question, and they are related to the fact that all of these points on this line are the solution to this one. And by the way, since there are an infinite number of solutions, and these are actually the same line, we say that this is a dependent system. And with linear equations, we in two variables, we have just seen the three things that can happen. The lines can intersect at a point, the lines could be parallel and you'd have no solution, or the two equations could really have the same graph and you'll have infinitely many solutions. But let's move on. Let's now turn to solving a system using the substitution method. Notice again we have two linear equations. We could in fact graph them, look to see where they intersect, and that would be the solution. But we're going to solve this using the substitution method. Recall that that means we need to solve for one variable in either equation. since I see the x in the second equation has a coefficient of 1, that seems to be the easiest one to solve for, so I'm going to solve for this x. But it really is a matter of personal preference. You could solve for x here, y here, x here, or y here. So I'm going to solve for x in that second equation. So when we add 3y, we have x equals 3y plus 7. Now here's where the substitution comes in. We're going to replace the x in the first equation with what we know is equal to x for this problem. This 3y plus 7 is going to be substituted right there, hence the name substitution. So we'd have 5 times 3y plus 7 plus 2y equals 1. And now we can just solve this linear equation. We'll distribute, combine our like terms, and finish solving. So we have y equals -2. That means the y coordinate of the point that these two equations share would be -2. Since they intersect at a common point, both of them having the y coordinate of -2, you can substitute -2 in either equation to find the x coordinate that goes with it. Or we could even substitute it into this equation. So you could substitute the -2 in here, here, or here. I'm going to substitute it in right here because we already have the x isolated. So we have x equals 3 times -2 plus 7. So that's -6 plus 7, or 1. So the solution to this system is 1, -2. And as I mentioned on the first example, when we were solving by graphing, you can substitute that ordered pair into both equations if you'd like, and double check that you have the correct solution. I'm not going to take the time to do that, but it's definitely something that you could consider doing for a particular problem. Let's do another problem. We'll do one more using the substitution method. And again, when I'm using substitution, I look to see what variable would be the easiest to solve for. None of them have a coefficient of 1, but this y has a coefficient of -1. So for me, I would choose to solve for that y. So we have 8x minus y equals -67. I'm going to subtract 8x and divide by -1. So we have y equals 8x plus 67. And again, we're going to make the substitution. This y is going to be substituted into the second equation. This was from equation 1. Make sure you get it substituted into the other equation. So my equation would become 2x plus 3 times 8x plus 67 equals -33. And now we can just solve our linear equation. Let's do that. Let's see, 67 times 3 is 201. So we combine our like terms. Subtract 201. So we have -234. And we divide -234 by 26. And you could grab a calculator to do that if you'd like. And when you do, you would find that the result is -9. But remember, we're looking for the entire ordered pair. Now we know the x coordinate of the point that these two lines would share would be -9. We need the y value that goes with it. Again, you can substitute the x in here, here, or here. I'm going to choose this equation. So we have y equals 8 times -9 plus 67. So we have -72 plus 67 And we'll squeeze this in, and we have y equals -5. So the solution to this system is the point -9, -5. Let's continue. Now for this particular problem, you could solve using the substitution method. Notice none of these expressions have a coefficient of 1 or -1, but that doesn't mean it's not doable. It just means it would take a little bit more work to solve for one of the variables. You'd be introducing fractions, but it's totally fine to do that. But I want to remind you of our third strategy that we're going to be talking about, and we're going to be talking about the elimination method. Also called the addition method. Both of those names are very common. Now, the elimination method says that if we have two equations that are represented here, we could add everything on the left-hand side of the two equations together, and everything on the right-hand side gets added together, and you make sure you set them equal. So if I were to add these two equations together, 5x minus 2y, -3x plus 2y, notice those y's disappear. They're eliminated. That's why we call it the elimination method. And we would get 2x equals 14. Wow, pretty quickly we get to x equals 7. And just as we did in the previous two examples, once we have an x coordinate or a y coordinate for the solution, we can substitute back into either equation we like and solve for, in this case, y. So let's substitute 7 into, you just pick whichever one you prefer. I'll substitute it into the first one. So we have 5 times 7 minus 2y equals 1. And we solve this equation, subtract 35. And we have y equals 17. So the solution to this system is 7, 17. Now notice what made this one particularly nice is that we just had to add those equations together and the y's were eliminated immediately. That was handy, but it is not always the way the equations come. So let's look at this next system. And we are also going to use the elimination method. Notice if you were to add these two together, these two equations together, we would get 4x minus 7y equals 27, which is not helpful at all. We need one of the variables to be eliminated. But notice what made that happen. We had coefficients that were exact opposites of each other. We're going to use that idea on this problem. We're going to force the coefficients of either the x or the y to be exact opposites. Remember, when you're working with equations, you can always multiply both sides of an equation by any number you want to, as long as you don't multiply by 0 and wipe out the whole equation. So I would like the coefficient of this x to become a -3. So I'm going to choose to multiply both sides of this equation by -3. Totally valid. Remember, it's called the multiplication property of equality. So our system now becomes -3x plus 33y equals -48. Make sure each term in the equation gets multiplied by that number. And I'm going to leave the second equation unchanged. And when I add these equations together, I get 37y equals -37. Divide by 37 and I get y equals -1. So I now substitute -1 back into any equation I like, and really any version of any equation. I could substitute the -1 in here, 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 wherever I like. I like the original version of this first equation right here. I'm solving for x now, so -1 goes in for y. So I have x minus 11 times -1 equals 16. So that's x plus 11 equals 16, or x equals 5. So our solution, make sure you're careful about the order in which you write the ordered pair. Our solution is 5, -1. And let's do one last problem using the elimination method. Remember, the goal when using the elimination method is to make the coefficients of either the x or the y become exact opposites. On this previous example, it was a little bit more straightforward because I happened to have a coefficient that was 1. But that's not necessary, and often they come looking like this. But my goal is still the same. Decide whether you want to eliminate the x's or y's, and it's just a matter of personal preference. I'm going to eliminate the x's, and the only reason I'm choosing that is because they're already opposite in sign. So my goal is to multiply each of the equations by a number that would force the coefficients to be exact opposites. In other words, find a number that both 5 and 6 go into. That would be 30. So I'm going to multiply numbers by numbers that will make this coefficient 30 and this coefficient -30. So that means the first equation is being multiplied by 6, and the second equation is being multiplied by 5. If I do that, I get 30x plus 18y equals 6, and -30x plus 20y equals 15. When I add these equations together, the x's are eliminated, and we get 38y equals 21. And we divide by 38, and we get 21 over 38. And I know often students get worried when they see solutions that look like that, but that's a totally legitimate, fine number. It isn't an integer, but that's okay. Systems can have solutions that look like this. Now I could continue as I did in the previous problem, substituting 21 over 38 in for y and solve for x. Totally fine. But I wanted to show you another possibility when using the elimination method, which makes it kind of nice if you don't want to substitute in this fraction. Let's come back to the system as it was at the beginning. 5x plus 3y equals 1, and -6x plus 4y equals 3. If I use the elimination method a second time, I can eliminate the y's this time and have the x value, and then I can put those two values together as an ordered pair for the solution. So I'll show you what I mean. We're going to now eliminate the y's. The goal is to make these be exact opposites. I know 3 and 4 both go into 12. So I'm going to multiply this equation by 4 to make it a positive 12. Now they do need to be opposites. So I'm going to multiply this equation by -3 to make that become a -12. So my system now becomes 20x plus 12y equals 4, and 18x minus 12y equals -9. And when we add these equations, we get 38x equals -5, and we get x equals -5/38. So we had these two entertaining values for our solution, but it still wasn't too bad to find them. We just used the elimination method twice. So our solution is -5/38, 21/38. and we have finished solving the system. I hope now you'll go practice those 3 strategies for solving systems.